You're almost there, halfway through the AP materials. You've got this! In this lesson, you'll learn about 3 sorting algorithms: bubble, selection, and insertion. Bubble sort is the simplest of 3 sorting algorithms, and the slowest. The bubble sort gets its name from the way the largest items bubble to the top or end. The procedure goes like this. Move the largest remaining item in the current pass to the end of the data as follows. Starting with the first 2 items, swap them if necessary so that the larger item is after the smaller item. Now move over 1 position in the list and compare the next item. Swap again if necessary. Remove the largest item most recently found from the data to be searched and perform another pass with this new data at the beginning step. Repeat the steps until the number of items to be searched is 1. To see how bubble sort works, let's try an example. The following program implements the bubble sort algorithm. Given a list of 6 values, the loop variables outer and inner will evaluate as follows. When outer equals 0, the inner loop will do 5 comparisons of pair values. The inner ranges from 0 to 4 and does the following comparisons. If this expression is true, then the values are out of order and a swap takes place. The swap takes 3 lines of code and uses a temporary variable temp. After the first pass, the largest value will be in its final resting place. When outer equals 1, the inner loop only goes from 0 to 3 because the comparison between 4 and 5 is unnecessary. The inner loop is shrinking. Because the presence of duplicate values, the algorithm will result in a list sorted in non-descending order. The selection sort also makes several passes through a list. On each pass, it compares each remaining item in the smallest or largest item that has been found so far in the pass. In the example below, the selection sort method finds the smallest item on each pass. At the end of the pass, the smallest item found is swapped with the last remaining item for that pass. Thus, swapping only occurs once for each pass. The logic of selection sort is similar to bubble sort, except with fewer swaps are executed. Again, assuming we have a list of 6 numbers, the outer loop will range from 1 to 5. When outer equals 1, we will look for the smallest value in the list and move it to the first position in the array. However, when looking for the smallest value to be placed in position 1, we will not swap it as we search through the list. The algorithm will check the indexes 1 through 5, keeping track of where the smallest value is found by saving the index of the smallest value to min. After we have found the location of the smallest value, we swap list outer and list min. By keeping track of where the smallest value is located, the swapping only occurs once. This makes it more efficient than bubble sort. Insertion takes advantage of the following fact. If A is less than B and B is less than C, then A is less than C. We can skip the comparison of A and C. Consider the following partially sorted list of numbers. The first 3 values of the list are sorted. The 4th value in the list needs to be moved back to the list between 2 and 5. This involves 2 tasks. Finding the correct insert point, and a right shift of any values between the start and insertion point the code follows. By default, a list of 1 number is already sorted, hence the outer loop skips position 0 and ranges from positions 1 to list size. For the sake of discussion, let's assume a list of 6 numbers. For each pass of outer, the algorithm will determine 2 things concerning the value stored in list. First, it finds the location of where list outer needs to be inserted in the list. Second, it does a right shift on sections of the array to make room for the inserted value if necessary. Constructing the inner while loop is an appropriate place to apply to Morgan's law. The inner while loop post condition has 2 possibilities. The value key is larger than its left neighbor. The value key moves all the way back to position 0. It can be summarized as this. If we negate the loop post condition, we get a while loop boundary condition. It can also be written as: the 2 halves of the boundary condition cover these situations. We are still within the list, keep processing. Value in list position -1 is larger than key. Keep moving left to find the first value smaller than key. Insertion sort algorithm is appropriate when a list of data is kept in a sorted order with infrequent changes. A new piece of data is added, probably to the end of the list. It will quickly get inserted into the correct position in the list. Many other values in the list do not move, and the inner while loop will not be used except when inserting a new value into the list. These 3 sorting algorithms are categorized as quadratic sorts because the number of steps increases as a quadratic function of the size of the list. It is also very helpful to study algorithms based on the numbers of steps they require to solve a problem. We will add code to the sorting template program and count the number of steps in each algorithm. This will require the use of an instance variable. We'll call it steps. The steps variable will be maintained within the sorting class and be accessed through appropriate accessor and modifier methods. You will need to initialize steps at 0 and the appropriate spot main menu method. For our purposes, we will only count comparisons of items in the list and gets or sets within the list. These operations are typically the most expensive, time-wise, operations in sort. As you type in the sorting algorithm, add increment statements for the instance variable steps. As you count the number of steps, an interesting result will show up in your data. As the size of the set doubles, the number of steps executed increases by approximately 4 times, a quadratic rate. Notice that the sorts we develop know how to compare integers. Comparison is built into the integer class. But what if we wanted to write a sort that could work on strings? You cannot use the less than on strings. Remember, you have to use the compare to method. If I am able to sort my data, there must be an order defined for it. Classes that have an order should have a compare to method. Java defines an interface comparable just for this purpose.